Right, shall we begin with the 2019 exam?
Sure thing.
Yeah.
Sounds good.
Yeah, I was like, maybe if people here have done 2019 already, then yeah, but sure.
I didn't do anything.
Fair enough, same. Read questions carefully. Don't worry, you know it. Haha, fool. Proper notation to net scalars and vectors. Okay. I'm gonna probably use overline in LaTeX. Huh. So derive the corresponding system of partial differential equations. So the following system of laws, they say that and then show us 4 different laws, each with 1 point. So I feel like I'm gonna fill this course. No, at the
If you
very
pay, I pay.
So let's see. Global conservation of hold derive the corresponding system of partial differential equations. Okay, so what I'm reading here is that for every single one of these, we need to turn it into a partial differential equation. Okay, so first thing I'm going to do, I'm just going to copy it over and we're going to start doing some random math. We'll see where we get. Because, Lord, I do not know the meaning of E and rho and H and mu and... I'm just... Like, I know how some of the math works. I don't know the intrinsic meaning behind them. Right, so this is 1. I have to get another enumerate. That's 1a. I'll just go... So it is epsilon 0 int and it goes over delta omega. So this is a double integral, so a 2D integral, you could say, over the boundary. So yeah, it's an integral in 2 dimensions over a boundary of a vector, E, whatever the fuck that may mean. Times a constant. And that is the same as an integral over the entire volume of rho, whatever rho is. Int of omega. Oh, and I should add a ds at the end here. Omega. Rho. Don't you love it when you have more fucking Greek letters and numbers?
Math, they say, no
Yeah.
numbers.
Huh. Where the hell did my document go? Oh, well, whatever. So the integral is... Is there a way to have a bigger integral sign? I think the slash integral is... No, that doesn't exist. I guess it's just having 2 of these. Yes, no. Yeah, there we go. Okay, so... Yeah, so we know these are the same. So the first thing that comes to mind here, to me, is turning this from a global conservation law into a local conservation law. Don't know why, just feel like it. So first thing I would do is use the divergence theorem here to say that this integral over the boundary of E is the same as the integral over the triple integral of the divergence of E, or whatever the fuck that it is. I think it's like capital nabla. No, it's the capital delta, I think. Which one is it again? Nabla squared or delta squared? Oh, I always forget which one to turn around. Is the original one, or is the divergence?
Nabla. You want Nabla now.
Okay, I want nabla, thank you. Nabla. Okay. Oh, this is Nabel. It's not Nabel, it's nabla. Hello? Oh, nabla is always capital, apparently. Yeah, so this is like the first thing that comes to mind here. Then taking the epsilon into the brackets, and then looking at the inside of the integral instead, because it's the same integral. So okay, so this is already, I believe, this is already a differential equation coming from the original, right? Because this is the double integral of E, or well, it's not the double integral per se, it's the fucking... I always see this thing as a double integral, which probably has many wrong meanings to it, but whatever. So this is just a factor times the double integral is rho at x, y. Or that double partial derivative at x, y. So yeah, so
I think now you've written it as the gradient of E, but when you apply the divergence, would it not become
Yeah, he needs to put the
the
dot product
divergence?
here.
There should also be a dot between the
Yeah,
nabla
yeah.
and the E.
Yeah.
okay. Hold up, I get called. Yeah? Sorry, what?
What, Habra, what is the other thing? It doesn't have the dot?
Yeah, between the because now
If it doesn't, if it has the dot, it's divergence, and if it doesn't, what it is?
it's the gradient.
Mm.
Yeah, now it's good.
Okay, and then also, of course, down here. I was gonna check my notes real quick, because
Yeah,
like,
it's correct, I think, what you
I'm
did.
quite sure it's correct there, but like,
Yeah, but what's the difference between gradient and divergence? Maybe someone I can explain in a
I
physical way or
think
something?
the gradient is
Yeah,
the change with respect to space of a scalar function, and the divergence is the change with respect to space of a vector function.
Ah, okay.
So when you apply the gradient to a
Yeah.
vector function, it becomes a
It was a
divergence.
scale. Ah, wait, okay. What? Okay. And what is the divergence of a vector function is a scalar? It is, right? Because the dot product of
yeah.
Yeah.
yeah. This is a scalar.
Yeah, so
It's
because
just
the nabla is just the shorthand for d
this vector.
delta x, delta y, delta y, delta z. So dot producting them just multiplies them, so it's delta ux, delta x, delta uy, delta y, delta uz, delta z, and then adding those up.
You just add them and it's a
Yeah, so
scalar.
the dot product here actually somehow makes sense. So yeah, here you would get a single number, and rho is also a scalar, so it makes sense to use the dot here, because if you don't use the dot, what happens then? I believe you get some weird fucking matrix.
No, that is the delta. This is when you have nabla squared.
Yeah, so yeah, nabla u, so nabla times a matrix is just the it's yeah, okay, of course, because it's like a
Shit.
vector times
This is the
a
gradient
transpose
of a vector.
vector becomes
Yeah.
this thing. So yeah, no, that does make sense if you think about it in the way of dimensions, because using the dot product here gives us using the dot product here gives us a scalar, and using matrix multiplication gives us a matrix. Okay, yeah. But yeah, so I think I'm not sure what exactly it is they want from us, but I think that if they're asking for derive the system of partial differential equations, and this is a system of partial differential equations, so
Yeah. Agreed.
my guesswork leads to this. This is what I would write on a test. Let's say it like that. Right. So actually, this is one thing I like to consider myself at least decently proficient in, like moving fucking numbers around in a way that makes sense. That's how I actually. That's how I survived the first. That's how I think I got
Calculus.
decent scores of the first assignment. Don't know what everything meant. However, I was moving some shit around, and the numbers at the end weren't completely horrible. So I think I got like an 8.7 for that one. Oh, what the fuck is going on? Oh. There's my boyfriend's phone that's ringing. Well, he's not home. Sucks to suck. Right, okay, so mu over delta omega over line h c dot apparently, okay, apparently that's how you write that, and that's equal to 0. Okay. So yeah, I think this I would just again apply the divergence theorem or whatever the fuck it's called.
Yeah.
And just turn this into the thing over omega, and then you get nabla c dot overline h c dot overline v. Do we need a c dot if the no? Okay, so this is only if you are doing it with respect to a vector, which does make sense. So it also means that here there needs to be a c dot, but not the lines after it. So let's see. Here does that make sense? Yes. V is no longer a vector, so this overline needs to go. Because that's shit that they will absolutely retract points from during an exam, I believe.
Yeah, and this question like this, that is like the easy ones.
Yeah.
They will.
Third int.
But you mean notation of vector, all this? He said he's gonna remove points.
Yeah. But I mean, notation, like if you know how to like work with this kind of numbers, then notation is really the only thing that's being done here. So yeah, move this into the thing. Can you just do that? Not even sure. I don't know. I don't think you can do this though. No, I don't think you can do this, can you? Because this is like the final result of everything is 0. But it doesn't mean that locally it has to be 0 as well. It can just cancel each other out.
I think you can.
Okay.
You can take everything out of the integral.
I mean, I guess the way you could reason about this is that you're just like taking the derivative of both sides 3 times. which
True.
I mean, it just seems kind of weird that if you take the integral, that's like saying that if the integral over an entire function, so that's like saying that because here, fucking for example, say we have int from 0 or from -1 to 1 of x to the 3 dx is 0, right? Because x to the 3 is an odd function. Oh, well, that needs to be in the fucking brackets. It's like taking derivative here and then going, well, yeah, so x to the third is 0. I feel like that doesn't make as much sense. Like, maybe I'm wrong, but I would love to know why. Because, I mean, it's the same thing we're doing up here. It's the same thing we're doing down here.
I agree
Yeah.
with you, but I think, yeah, no, I agree with you.
Yeah, because I know that this is allowed. Why is this allowed, actually? I guess because this is true. No, because we only said
I
this is
think
true
he
for.
explained this in the first lecture.
I'm sure he did, but like the first lecture, I didn't understand anything.
Neither the last also I did.
Yeah,
He
so
said if this holds for any omega, then the local conservation law is, and then he removes the integral.
yeah,
And then he probably said something in the lecture
I
like,
don't think he told us why this is like the
mm,
case that it's allowed.
no, he just said it is. Trust me.
Source, just trust me, bro. No, oh well. Okay, oh, sorry, give me a quick second. Whatever. Okay, so yeah, I guess that I'm just gonna assume we can do this, and if I'm wrong, which is very possible, then we'll learn from it from the answers. How's that sound?
Yeah, that's a good way to learn.
Yes, because I mean that's why we're doing this. If we already knew all the answers, then why were we doing this? Oh god. Minus. Okay, for this I'm just gonna like keep two windows open, and I'm just gonna minus integral over c, whatever c may be, of overline h c dot d overline r plus epsilon 0 frac d or delta. No, this is d because we're not partialing yet. dt of int over sigma. Don't know why sigma is showing up here, but sure. Of overline e c dot d overline s equals negative integral over sigma again. I have no idea what sigma is even. Oh, the boundary curve of the surface. Okay, well those sure are words.
No.
Okay, recompile this and see if this is right. So h dot dr plus epsilon 0 derivative over e times ds is, oh, I put sigma here. It should be sigma with a capital of the flux, whatever that may be, over ds. Okay, so the question is correct. Now the answer. First of all, what
Yeah.
is c? Because I know what omega is. C is the boundary curve of the Okay, so what we're doing is instead of doing a instead of going over a domain with a boundary surface, we're going over a curve with a boundary, or with a surface with a boundary curve. So I believe we're just dropping down
One dimension.
one dimension,
Mm-hmm.
which yeah, C is the boundary curve, and okay, yeah. I don't think that this is something we have had per se. I think we might be able to like figure the math out because it's probably similar to boundary surface of a domain, but like, yeah, I'm not sure if this is something we have had to begin with, which makes sense because it's like 3 years ago. But we'll give it a try.
Yeah, this one.
Right. So we have a so. Okay, what I'm just gonna do is I'm gonna do a chat move and just assume shit. And my assumption is that the divergence condition holds for one less dimension. And I'm just gonna go. This is the same as the double integral over omega sigma balls, of nobla. Is it nobla? Yes. C dot h. And then it goes over S instead of R.
Yeah, I have the answers open here. So
I'd rather like try and figure it out, and
okay.
then like when we're done, we'll go through the answers.
Okay. Okay.
If that's okay by you.
Yeah. I close the answers.
Sure. Yeah, so what I'm going to do is I'm going to just pull this inside, and I'm going to remember that this becomes, instead of a normal derivative, it becomes a partial derivative.
Yeah.
So then...
And now from what we have there, we can do what we did before. Just remove all the integrals and
Yeah.
just
So...
keep the rest, but with partial.
Yeah, so this is delta t over line E. Let's see if this still makes sense. Oh, it doesn't, because I miswrote delta. Delta over delta E. Yeah, I'll just... Yeah, I probably should put some brackets around to show which part is being integrated, but I really can't be arsed. Don't you love, like, having a full line of latex, which is nothing but blue? My favorite. So yeah, then I'm gonna pull this negative nobla over line H into the other one. And then remove this integral. Oh. Let's see if that still makes sense. Negative H plus this part is that thing. Yeah, and then I'm gonna remove the integral and also pull the negative sign into it. And then we are left with this. Okay. And then I'll do the same trick down here. I mean, it's gonna be mostly the same, really. Time to fucking write the entire thing out again. go. Oh, interesting. Did I put it above the... Yeah. That's where my document went. This would be... I'll remove the section. Okay, there we go. And then down here I'll add an item and I'll go fancy math. Int over C over line E C dot D over line R plus mu 0 frac B dt int sigma over line H C dot D over line S is 0. Yeah, looks good to me. There's probably a way to do over arrow or something, but I mean...
You can do vec
Vec.
/vec.
Yeah. We should use vec instead of overlined. Looks fancier. Oh. Okay, please, someone fucking standardize whether Control R or Control H is replace everything. I swear to God. Where's search and replace? Okay. This should better have a search and replace function. I fucking Notepad++ it is. And then replace overline with vec. Hell yeah, look at us being fancy. Okay, so yeah.
Also, only for your reference, but it's not small delta, it's partial. Back. You know what I mean?
Is there a difference?
Yeah. So how do you say? Call it backslash partial.
Huh.
Oh, someone who knows numerical methods just arrived.
They look like the same symbol.
No, crazy. Is this
No,
the
you're
same
right.
symbol?
You're right.
You
You're
was
right.
a Greek
It goes backwards. Yeah.
partial.
Of course not. I need to see it.
Yeah, the Greek woman said it's not the same thing.
Which letter is the partial one then? Or is it not?
Not a
letter?
Greek one.
It's just a fucking number. Okay. Or a symbol. Okay. Well, today I learned. Right. Time to... I'm probably gonna fuck it up a few times, so please correct me if I do. First thing I'm gonna do, I'm gonna turn E. I'm gonna do that thing we did earlier where we assume that the divergence theorem holds. Which is always the best thing you can do, make assumptions. It goes over sigma then. And it becomes a vec R, and there's also a nobla C dot involved. Wait. It's not V, it's S because, yeah, okay, no, that makes sense. Because we're not talking about volumes. I could, like, put this to the other side and then put it aside, but it's the same as just doing it right here, so I'm just going to do it right here because I'm lazy. And then this becomes partial.
BRB, but you
Sure.
can continue doing this.
Okay, lovely. Partial. Who? Oh, I put this after the vec age. No, that should be there. Okay. Okay. So that looks to be somewhat logical at the very least. How many questions are there? Oh, 6. What? They just give us theorems and definitions? Yes, please. Alright. Consider a boundary value problem. So, is this just me, or is this the same as saying, oh no, use a fucking single function? No, yeah, fair. Okay. So this has to do with thing 1. Which honestly I have long forgotten. So I'm just gonna be sneaky. I'm gonna lie and cheat and just look at my notes. But yeah, we are talking about a second order PDE. But we can't really say this because we have 3 variables, don't we? Or can we extrapolate this to multiple? So yeah, I'm just gonna assume that we can, and A1, 2 are 0 because we don't have combined things. So then I'm assuming that this equation is elliptic. Don't know if that helps us because I don't know what elliptic hyperbolic and parallel do for us. But at the very least, I would say it is elliptic. Come out.
You.
Goed, doe een session. Ik doe een session.
Ah, nice.
Ja.
Good luck. Wanneer is de volgende date? Wanneer is de volgende date?
Morgenavond.
Ah, nice. Denk je later?
Ja.
Nice.
Ja. Hoe ging ie? Hoe ging ie?
Ik heb om 3 of om 5 vandaag. is echt
Dan.
een heel...
Dat zeg je helemaal niks.
Ja. Onze vak hebben geen overzicht. Punt. Helemaal geen. Dus het is maar heel moeilijk om erop te komen wat ik heb. We gaan zien.
Ja.
Veel geluk met je session, Pik.
Thanks. I'm back. I was looking at my notes for the lecture. Okay, so that actually doesn't tell us much. I mean, yeah, it tells that it's a steady state problem, so that's good. Determine the sign of the solution.
You can use the theorems in the appendix to determine whether the solution is sub or superharmonic to determine the sign. That's what they say, right, in the question, that we have to use only this theorem.
They say, assuming exist and using only the yeah, true, fair enough. Answer all these questions. Okay, so only the sign of the solution. The sign of the solution is, suppose that, okay, so first of all, let's see if it is superharmonic, subharmonic, etc. So, you are is 0 on the boundary, and everywhere else it is the divergence. Okay, so first of all, isn't what does this exactly mean again? Because I believe that nabla, or no, this is
Yeah,
delta.
this is nabla squared.
Yeah, so
So it's this. Okay, this is, well, plus nabla squared you equal where?
yeah. So then f if we equals negative f, since f is everywhere negative, f becomes everywhere positive. So it is superharmonic, right?
I guess, yeah. I agree.
Yeah. Okay. So if it is superharmonic, its max or its minimum is at the boundary.
Yeah.
And we know that the boundary is 0. So if its minimum is at the boundary is 0, the function is positive.
Yeah.
Okay, so then I'm gonna item begin enumerate. We know that let's see, it's nabla.
Yeah.
Or
You can do, if you want to do double integer instead of doing int, you can do like double I int, like if, or triple with triple I.
yeah, int. Okay, thank you.
Yeah. Or int for triple.
Yeah, so is minus, this is delta. So we know that capital D, delta U is negative F with F greater or smaller, dus lek 0 for or I'm just going to say on omega because I'm too lazy to give them variables. Thus, I'm just going to call this F2. Or here, I'm just going to go negative F with negative F greater or equal than 0 because they want me to write down all my substeps. Thus, the function is subharmonic question mark? Superharmonic. One day I'm gonna learn this by heart. Today is not that day. According to definition, or is it theorem 1? I think it's theorem 1. Yeah, theorem 1. According to theorem 1, this means that the boundaries are the minimum, or boundaries contain the minimum values. We know the boundaries to be 0. Therefore, the entire function is positive. Okay, that doesn't sound too unreasonable, I hope. Fucking. Some quick formatting fixes. Okay, so according to theorem 1, this means the boundaries contain minimum values when the boundaries to be 0, therefore the entire function is positive. Yeah.
Yeah.
I assume that boundaries are the
Which
minimum
is
value.
yeah, this is theorem 2. We have minus delta u is bigger than 0, and we also have the u is 0 in the boundary, so u are bigger than 0. So yeah, A is done.
Yeah, I'm just gonna. Then I'm gonna say we know definitely the entire function is positive by theorem 2.
Mm.
Yeah, you're right.
Or 0.
Yeah, I believe positive includes 0 in this definition.
All right.
I think.
That
Whether,
can be.
whether positive numbers include 0, don't get me started.
That's
But
a different
if a function is
discussion.
positive,
Is
I do believe includes 0. I believe actually a negative function also includes 0.
yeah. It's not positive nor negative.
Okay. If possible, determine the location of the minimum of the solution. Well, the minimum is on the boundary. It's on the boundary. Oeh, hard werk, strijden. Also, I'm going to check if I'm recording. I am, lovely. If possible, determine whether the solution is unique.
No timer today.
Oh, that's a very good shout. Yeah, that's on me. Live split. What I can do is I can see how long the recording has been running because I started when we started, and I can start the timer at that value. What? I think I waited at the beginning for like a while. Are we already busy for 45 minutes?
No, maybe 30.
Yeah. I think I waited 50 minutes at the beginning, so I'm gonna set it at 30. Can I do that? Start timer at 30 minutes. Is it seconds or minutes? Seconds. Yeah, that's not good. Edit. Editable. Is this the way? Yeah. Okay. So then I can go start. Okay, and now we're going. If possible, determine whether the solution is unique. Oh, I always love the uniqueness proof. I just really find them pretty. Then if it is connected and there's an internal point where it reaches its minimum, So on that point, on the thing itself, it reaches minimum, then it is constant. Yeah, makes sense. So I don't think we can say that. I don't think we can say that it is constant yet. I do remember how you prove this though. So I believe it is with when you go. Say we have two solutions. We are going to subtract them from each other, and the value is 0. If you subtract them from each other, therefore they are the same
Yeah.
solution. I believe that is approximately the layout of the proof.
I think so too.
Because I've definitely done this before, right? Like in assignment 1. And he's also
Yeah.
done so in the lecture. Let me see. I'm just gonna have a look at this, see if. Because I mean, I know that we can
Yeah, I
say
can't
this,
find.
but we can't use this, so we're gonna have to derive this on the spot. Yeah, so I believe that the way he did this is, although we had ux is 0, but I believe that is 0 is a function. Yeah, this should be all that you need. I mean, yeah. So this, if we could use this theorem, then we are like done almost. But we can't.
And you can. No?
No, because this,
no,
the,
you
the
can't.
entire point of this assignment is that you can only use these theorems.
Yeah.
I'm gonna be rude and I'm gonna like quickly have a look at what I handed in so I can like see the gist of that proof.
Yeah, that's a good idea.
Because yeah. Yeah. So okay, I see the idea of this proof. So you would literally, okay, I'm just gonna type shit and I didn't get full points on this proof, so I might be doing wrong, but I'm just gonna type shit, and if you see something which you just completely don't agree with, do tell me, because that's how we learn. Say we have two solutions for f, call them f1 and f2. Let's subtract the solutions of both of these from each other, or the equations. So then we get, because we know that wait, no, we have f. We want u1 and u2, because u is the whole thing we're trying to look for. So we get delta u1 minus delta u2 equals f minus f. we get, because these are all at the same points, we can just say a 0. And then and then there was a way to show that this just equals 0. That was, I believe, the rough idea of the proof. Difference. Gonna pull up my fucking homework again. Because he did do this in class, and I was there, so I have seen like the reasoning behind this proof before.
Yeah, I think it's this, and then delta U1 minus delta U2 is the same as delta U1 minus U2. The only way for that to be 0 is U1 equals U2, which
Yeah, but
means it's...
so the thing is, then we can just say that for every function ever. So I'm not sure. Because so far, I think I agree with this still. But I don't think we can just pull everything inside of one. No, that is what I did in my notes.
Yeah, it's what I did in my first assignment.
I guess at the very least we can say that the delta of the difference is a 0, but I don't think this automatically leads to the fact that it's the same function. Like we first have to there's something else to this. So we're sure this is delta, not blah. Yeah, I guess. Yeah. Yeah. I feel like, for now, I'm just gonna say that this is true, but I definitely feel like this is wrong, and I think I'm just gonna wait until we see the answer and then see there what happens. But yeah, I wouldn't be happy fitting this in an exam, but I'm just gonna say that I'm just gonna say this for now. Yeah, well, right.
Gerb sent his on the chat because he can't speak. He sent on the chat here his solution for the assignment. Show the uniqueness of solution.
Yeah.
Damn. Yeah, this exam is gonna be difficult.
Yeah, so I do agree with that. Like the difference has to be greater or equal 0 and lower or equal 0. I do remember that. Yeah. For now, I'll just do this and then we'll continue. I don't think thinking about this more now is going to give us a lot more information,
Yeah.
especially since we have to do 2 exams. Or at least I want to do 2 exams, if possible. Okay. Consider this boundary value problem. So find the exact solution of. I mean, here I would literally just start doing algebra.
Yeah, me too.
So we know that
Integrate
negative
to
u thing equals x squared. Therefore, we know that negative u is the integral over dx. And I could like do that again directly, but I'm like, hello. Oh, I see what the issue is. Okay, and this would then be a third x cubed plus c, because of course. Plus c1. And then this becomes negative u is, and I probably should like just move this negative sign to this side, just because I'm not entirely 100% sure how negative signs work when you differentiate one side. I think it's not, I'm 99% sure it's fine, but better be safe than sorry. And this becomes, so this is 1/12 x to the 4th plus c1 x plus c2. And then we can use this to fill in the fact that u0 is 1. Which gives us 1 equals C2. Well, lovely. So we have C2. Use the fact that U1 is 1. Fill the rest in here. 1 is C1 plus 1. So there we go. Negate 1, move this to the other side of the equal sign. 1/12 is C1. So then we get solution is this with the constants filled in. Probably a way to do it with matrix stuff, but like, come on, I might as well do. This math is quick, so I might have made a mistake, so I'm just going to check it real quick. So for 0, this gives us 1. For 1, this gives us 1. I can't argue with that. Yeah, okay. This sure is a double differential equation, which gives you... just to check that that differentiating it twice gives us x squared. Differentiate once, this term vanishes, or this term is minus 1/12, this term becomes 1/3 or 1/3. Differentiate twice, this term vanishes, it becomes...
I got the same.
Yeah,
I
no,
got the same.
this really, yeah.
It's correct.
Use
1.3.8.
Use Taylor series to derive the central approximation of U double
Nice.
prime on a uniform grid. I'm just gonna. It is one-dimensional, which is nice.
Yeah.
So I have never been the best at these things, so I'm just gonna try. So we know that x can be approximated by Let's see, Taylor series. I'm gonna try to remember this. If I haven't thought it up in like a minute, I'm gonna look it up. But so this is approximation only at xi. So it's xi. With plus xi. Let me first fucking put this in code block. Derivative at I over 1 plus. Where's 2 already? No. Right? No, I'm just making shit up at this point. I'm just gonna look up the.
You need to use Taylor series to
Yeah.
extend the ux is uxi plus derivative of
So
uxi.
I know that. I just don't know the Taylor series by heart. I have never bothered
It's
doing
just
it.
factorial. It's just normal plus the derivative. Dot times h plus the double derivative times h squared divided by 2 factorial. Then it's always the same. Then 3 factorial, 4 factorial.
Okay, so it is f at point A. So yeah, so of course this would be fx. Because I'm like, that's what we're doing here. Is f at xi plus f prime at xi over 2 plus f double prime of xi over. So it is. I know it's factorial. I'm just very lazy. So it's 1, 2, 6, 624. Yeah.
Yeah.
6 plus f triple prime xi over 24. And this is this is like
I think you have
fx
your.
minus.
So, I
Still
think you
missing an
skipped
x
one.
minus
Can I?
the x1 term.
It's just age. It's just a step.
Yeah.
And you have your things are a bit shifted. So the divided by 2 should be on the second, and divided by 6 on the third. The first derivative is just divided by 1.
Yeah, true. Can't argue with that.
And yeah, you have to multiply by age. So the first derivative you multiply by age, the second derivative you multiply by age squared, and so on and so forth.
So that is because we're squaring the difference between x and So times h squared h cubed dot dot dot. I'm just gonna say dot dot dot, so that like they can approximate.
Yeah.
So they didn't tell us like up to what level of approximation, right? Yeah, no, just derive the approximation.
No, but there is a. Let me think. Yeah, I don't know until when we have to do.
Yeah, so what I'm just gonna like say that they know how this continues. I know how to like chop it off. It's just they don't give us a point where they want us to. Yeah, and they want the negative of this. So sure, I can take the negative. Actually, is that the case? Yeah, the negative just distributes. I think. Oh, no. So what I get it again. What we need to do. So
You
we're
want the
not there
second
yet.
derivative.
Yeah. So we are not there yet. We need to like get the second derivative out of there. So I'm gonna put fx, and that's at this side. And I'm gonna take this one to the other side. Don't know if that is what we need to do yet, but that does seem to make sense. So then we get this. So just literally move this here, move this here. Then we're gonna multiply everything by 2 because we want to have not this fraction, but we want just the second derivative. So it's 2 plus 2 plus 2 plus 3. And then we divide by h squared. So we get 2f over h squared.
Center difference, there a difference between 3 points, so you should get an OH squared approximation.
H squared. And this one is going to be over h alone.
So I need
because
until
there's
6.
Hmm?
Kirby is saying something there in the chat that since it's central difference, we should be order of h squared approximation.
You can't construct approximately more accurate than without using more points. Yeah, that's true.
No, probably we have
But
to do this
so
until the 6.
So they don't really say that you need to only use 2 points. So, I mean, maybe that's in a definition of central difference, but technically you could go further. But I'll just do it for 2 points.
Yeah, I think he says that central difference implies, yeah, central difference is an order h square approximation. So it's the definition of the thing.
Right. So far we have this. Where everything else after this is OH squared. But I'm like, what can we do with this? Because I know that in their version, the fx just fell away, which, you know, is almost required. Write as a system of linear algebraic equations and solve that. So I definitely have how to do this in my notes, but I kind of want to see if we can do it without notes.
Yeah, I think
Because they definitely did something else here. I remember going, oh, that's a cool trick that they use. Yeah, that is definitely true.
yeah, the Taylor also has to be until 5.
Construct the metrics from your Taylor expansion. No, so there's more to this than that, because in that version, so that version that you have doesn't have the FX. They were doing like a they had a very smart way to get rid of the FX. I believe that they you don't need to get rid of that. Yeah, I mean, I know that the answer is in the slides. For sure. Does a difference have to be negative h? So it's x minus
Yeah.
x plus
So
1, so that's negative h. Okay, that changes a few things, and that's what we're missing. So, so this becomes negative h, and then negative h to the third, because that is also one of those. So here it is negative and negative to the third. This one's plus and the other one's negative.
my God, I'm writing my handwriting. U for age, they all look the same. Makes sense.
So let's see. They have the FA, yeah, and FX. Okay. So I believe that what they did was they used the fact that there's an FA minus FX here, and they used that as a sort of approximation, I believe.
I think you did from that. You have that first formula that you wrote there. So you should write this until order of age 6, just because we need the age 2 in the end, and we're gonna divide everything by 8. Actually,
Because so here we have h. So everything after here will be h squared. So we can say that this is this dot dot dot.
yeah,
We
yeah,
can say
yeah,
that this
yeah.
is
Order of age squared. Okay.
plus o h to the fourth here, and then we can go plus oh to the fourth here. We can go plus oh to the fourth here.
Yeah.
Turns
So this
into
is for ux, what you did, and now I think we have to do for u I plus 1 and for u I minus 1. So we're gonna have 2 equations.
yeah, I believe they had two equations. They added them up, and that canceled shit out. I think that's
Yeah, it's gonna cancel all the, say, odds, because the ui plus 1 is
yeah, I believe that was approximately what they did.
yeah,
Yeah.
because ui plus 1 is the same as x I plus 1 minus xi, and ui minus 1 is xi minus 1 minus xi, which is minus h, so they're gonna cancel out for the odd ones.
Mm-hmm. Um, so the method you outlined might work, but I'm too dumb to do that. I don't understand what your method is. And I think I'm talking to Gerb, so I'm gonna try to do it the way that they did in the lectures. If that's okay by you. If you can make a write-up of your method in Overleaf and send it, that'd be lovely. But I don't think it's how I'm gonna do it.
Yeah, I don't understand how Gerd does
Yeah.
things sometimes also.
Black mathematics. Yeah, agreed. Yeah, so let me just check if it makes sense that everything has the thing that it does. Yeah. Okay, so this is for, instead of xi, yeah, I'm going to say this is xi and this is f. So this fx. So this is fx approximated from fxi. So yeah, for this, the h's are positive. If we take x to be x plus 1, and otherwise they're negative. And I think that's the addition that cancels. Yeah, so now that we have this, I'm going to say now we approximate for x I plus 1 and x I minus 1. So this becomes xi plus 1, xi, and for x minus 1 we take the h's become negative.
Mm-hmm.
So this sign is the same, this sign is the same, this sign flips because there's an h down here, and so does this sign. So flips. And I go add these two approximations, and we get a whole big ass formula, namely negative 2 fxi1 equals, and then this is frac 4f, because these don't cancel out. This is a 4f because these don't cancel out. Oh wait, no, this is wrong. So this is 2, and this is minus another 2. And then plus a 4, and then these two cancel out because that one is negative, the other are positive. And if you look at this, this is exactly what we want. Because if we now divide by 2, we get our definition that we know from the book. Hell yeah! Fucking look at that little smart motherfucker. Yeah, okay. So this is the negative double approximation is oh, I got pinged in my minor project group. Deadline to deliver was
Seems correct.
yeah, so this is correct. Because
Yeah.
I know that's the formula.
That's good.
Yes, it is. I love it when math works out. Right, so item number 3. I am gonna have to learn the fucking McLaurin series by heart, or the Taylor series.
Yeah, I think also now where you say there, now we approximate for xi plus 1, xi minus 1.
Mm-hmm.
In the f, the first f also needs to put xi plus 1 and xi minus 1, right?
No, so we are approximating xi
xi.
from
Okay,
the viewpoint
okay,
of x plus 1 and x minus 1.
Okay.
Yeah. Okay, lovely. Divide them into 5 equal intervals, apply, discretize them, provide most of discrete equations in the matrix form of the linear algebraic problem. Okay, so first I'm gonna just write down all the x's. So x goes from 0 to 1, both exclusive. Oh yeah, that's because this, it is inclusive, but the edges are not in this range. Yeah, okay, no, that makes sense. Yeah, right. So I'm gonna go vec x is, oh boy, begin B matrix, and then I'm gonna go. It is, so it's 5 intervals, so there's 6 values. So it's 0, frac 1, 6, frac 1, 3, frac 1, 2, frac 2, 3, frac 5, 6, 1. So this should be our x matrix, or our x vector. Oh, this is not well established. Okay. Why is this not? Do I have to use a fucking different package to have block matrices? I think I do. Give me my matrices back. I think it's one of these two. Yeah, there we go. Look at them. It's not perfect because I'm using fractions, but it should be good enough. Although for some reason it's not showing my vector. Oh, that's because this is not in a code block or math block. Okay, so we've got that. We can say that our
What? Why? I think
so
you have 1.2 many. You
so
have 4.
it is 5 equal intervals. So there's an interval from 0 to 1, 6, an interval from 1, 6 to 1, 3, an interval from 1, 3 to 1, 2, an interval from 1, 2 to 1, 2, 3, 2, and an interval from,
Okay.
wait, 1, 2,
You
3,
just counted 6
6,
intervals.
7. You are right, and I am wrong. So this is going to become fifths, which makes sense because 0 is in there. Imagine fucking using 0. Okay. Good catch, good catch. Fucking, yeah, on me. Right, so indeed, 1, 2, 3, 4, 5. Okay, yeah. Didn't realize the fact that we have 0 there, of course. So that's that. Then I'll write A out next, which is always my favorite thing to do. A is begin B matrix. Oh, matrix. So it'll be. So we want the double negative integral. So that becomes 2, ampersand 1, ampersand 0, 0, 0. Oh wait, we don't want the. No, yeah, we do. So it's 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. 0. 1 or negative 1. This shouldn't be 1. It should be negative 1. 2, ampersand negative 1, ampersand 0, 0, ampersand 0. During the exercises, I wrote a fucking Python program to do this for me because I'm very lazy. But
Yeah,
for now, it's smaller, so it's not worth it. Negative 1.
I did too.
Base 0. Negative 1, ampersand 2. Wait, no. Negative 1, negative 1, and the last one, 0, 0, 0, 0, 2, negative 1. Right. Big ol' fucking matrix. Am I wrong? Yes. These two should be around, turned around. Okay, and then we can go F equals I'm gonna just write it as vec F because I'm fancy equals begin the matrix, and then it is 1 plus.
Are you sure you should put the boundaries also in this matrix? I think it's only the internal points.
Not
I
entirely.
don't
I
think
was thinking
0
about
and
it as
1
well.
should be there.
Um,
Because I remember it's in the assignment that was directly, we were just using the internal points.
yeah, I'm thinking about that right now, real quick. Yeah, and then so this one and this one will turn into those boundary conditions. Yeah, you're right. So 1, 2, 1, 2, 1, 2, 1, 2. So this becomes our smaller matrix then, and then this becomes this, and our vector f becomes f. I'm gonna call it f1 because it's not f0. And then this thing needs to be added, which is 0 times 1. Or hell, I'm gonna say plus f0 times u at 0. Well, I'm gonna write u0 equals f1 plus 0. No, this is not entirely right. this should be x0 times u0. And it shouldn't be u0, it should be f0. Jesus Christ, good morning. Because it is, after discretization, we get a, oh no, it's a times u, or a matrix A u equals, hold up, I am fucking clouding. Yeah, so f is this thing. So we can fill in f. We don't want f, we want the boundary values. So we know that a times, or a matrix multiplied u equals f. Yes. So this should not be x0, this should be u0. And we know u0 to be 1. Yeah. And then it is multiplied by f0, which is okay, so then it's this x value that's wrong, because this should be u at. So I'm gonna call this just u1. That's it. I feel like I'm doing it slightly wrong though. Just to check, I'm just gonna real quick, because turns into my brain is fucking
My
glitching.
God, can't even understand what you did there, Gerb.
Yeah, so it's AU equals F. That's the original fucking equation that we're trying to solve, right?
Yeah.
AU equals F. Okay. I'm just going to think out loud right now. So, since AU equals F, and
f is x squared. We also
yeah,
know that.
so yeah, so we don't need the x factor
No.
at all.
No.
So this can
No.
just go. So this will become U is.
I did here.
at-
I think. Well, the question asks for you to write the equations, but I understand that you don't want because you're writing LaTeX.
I mean, I will, or like, what are you talking about? The amount is like writing down the 4 equations one by
Yeah.
one. Yeah, I'll do that when I'm done with this.
Okay.
Not the end of the world.
But I don't know if it's. I don't know. I don't know how to see f without writing the equations myself. But let's see if maybe you come up with something interesting there.
Yeah. Yeah. We'll see. So this will become. So we know that if we were doing it the lazy way, which is wrong, because we're not thinking about the boundary condition or the boundary at all, we would get this. And I'm just going to say equals, and this will be equals. So f1 will be 1 minus 1. No, wait. Yeah, so this is just x squared. So this is gonna be 1 over 25. This is gonna be 2 over 25. This is gonna be 4 over 25. No, that's wrong. It should be 2/5 becomes 4/25, 3/5 becomes 9/25, 4/5 becomes 16/25. There we go, that's the math checks out. Okay, so this is if we're being lazy, and we're not. including the boundaries, and if I
Whoop.
actually write my fucking thing correctly, what is the issue? The issue seems to be that I'm not closing this tag. Recompile. Yeah, okay. So we have our f here, which does not include the boundary positions which are let out here. So
Yeah.
to get our u values, or it is u times a equals f. So usually we'd have a u0 here. So f1 needs to be negative, and then it is u0 times -1, because that's what this value would be. So what I'm doing here is I'm mentally extending this to be six columns long,
Mm-hmm.
because that's what you do. Like this thing could be 6 columns long, but we don't do that. So I'm mentally making it 6 columns long, putting it on top of here. So this would be -1, but that -1 gets put to the other side. So it's plus u0, and at the end it's plus u5. Which is because at the end as well, you would have this would be 0, 0, 0, 0, and here it would be -1. So it would be -1 times u3 plus 2 times u4 minus 1 times u5, but that -1 times u5 gets put to the other side. So if you do that, we get plus u0 and plus u5 here.
This that you're dividing by 25 there is just the 25 that was multiplying the matrix before, right?
So what I'm doing here is because f
The
is
h
x squared,
squared.
right? Yeah.
Mm-hmm.
And we know that x1 is 1/5, x2 is 2/5, or is 2/5, 3/5, and 4/5. So I'm squaring that.
Squared.
Yeah.
Yeah. All right.
And we know
And
that
also okay.
and we
But
know
then
that
you
x0 and x5 are 1. So this
okay.
can be simplified to be +1 and
Yeah.
+1. So I can say that this entire thing is 26 and this is 41. Which might be less clear,
Yeah.
let's say, than keeping it out, but I like fractions.
Yeah. I think
Um,
the only thing you forgot is the matrix alpha A should have 1 over h squared there also outside.
That is
I,
definitely true.
I think that's the
Always
only.
forget
I
that.
think.
Yeah, no, true.
Yeah. But the
Um,
rest I got the same as you.
so this is 1 over h, and h here is 1/5. So this is 1 over 1/5 is 5.
25. It's h squared. Yeah.
Hmm? Oh, it's h
H
squared?
squared. Yeah.
25, yeah. So then this becomes...
You just put outside, it's
yeah,
fine.
that's the easiest way to do it. I agree. 1 over 25,
Well,
yeah. So that
no,
25
no,
doesn't...
no. 25. It's
Oh yeah, it
either
is
1
25 or
over.
1 over... Yeah, you're right.
Yeah.
No, yeah, true. So
Yeah. Okay.
and that doesn't have
Deal
to
with
do with
all
this
of this.
25. Well, it
No.
does,
It's
but very tangentially.
true.
Okay,
It
so
does indeed.
yeah, and then we write out because they wanted both forms, just because they want your hand to hurt when you're done doing this exam.
Yeah, yeah. So you don't leave in 20
then
minutes.
you do, yeah, exactly. So you go u1. Okay, I'm just gonna and for the equations. So I know that these are like doing this is not going to add anything, but I'm doing this first of all because they ask for it, and second of all because this will like be a mental check to see if we're doing everything right. So it is u1 or 25 or no 50 u1 plus or minus 25 u2 equals 26 over 25. This isn't actually that bad. My fucking latex working properly. Okay, so it is minus 25 u1 plus 50 u2 minus 25 u3 equals, and this will become 4, this will be 9, and this will be 41. And this will be minus 25 u2 plus 50 u3 minus 25 u4, and then it is minus 25 u3 plus 50 u4. Right. And this is our system of equations that we would solve. And I get the system of equations by just literally writing out U A equals F. To make it a bit more readable, I'm gonna say, gonna put an end line here. They also asked for the equations where I go, A vec U equals vec F. So that's the equation. Is my equation gone? What? Oh, that's because I'm doing it. That's the right spot. Slight bookkeeping later, and we've got our answer, I think. Yeah. Right. 1 point, by the way. Just wanna say that.
Yeah.
Use A and B to divide the numerical value of the local approximation error for all grid points. Oh god, the fucking error. Fuck that. Oh, actually, no. That's very easy. Numerical value of the local approximation error for all the grid points. So that is literally just we want to know this h squared term. So we're literally gonna we know this term, right? So then we're gonna go for u1, or am I gonna say f1? I'm gonna say f1. No, I'm gonna say u1. So for u1, exact value is so the exact value is 1/5 into this function. So that is minus 1/12 plus 1/5 to the 4th. Could grab my calculator, but whatever. Plus 1/12 times. There should be a times as well. Times 1/5 plus minus here? Minus a. No, the first one is a minus, second one is a plus. Plus. And then plus 1. Yeah, I'm gonna go to Wolfram Alpha because that will give me a fraction back.
Yeah.
Jesus Christ. Well, sure.
Is it
buddy.
correct?
I mean, probably because like this to the power 4/5 times 1/12 just gives you giant fucking denominators. Yeah, no, I don't see why that wouldn't be correct.
Okay.
Yeah, so this is slightly above 0, and the next one should be more above 0, and then it's going to go down again. 1906. The second one being 1875. Approximation. I'll do that. I'll just write this out for every single one, so at least have some baseline to work on. So 1, 3, 4, and for 2 it is 2/5. There's 2/5. So there's 1 point. Or no, 1, 2. Uh, 8, 9 over 1250. therefore 3 over 5, we get 1299 over 1 to 50. Does that make sense? Because I feel like this function should be symmetrical, no? There's a difference of 10 over 9. Or 10 over 1250. Huh. Oh well, I'll trust Wolfram Alpha. It's approximately symmetrical enough, I guess. Yeah, there is like a slight offset to it, which is very weird to me. Why doesn't it? Oh. Probably should have checked this before I wrote them down. Okay. So the approximation for U1 becomes is this correct? I think for all this, like, we aren't talking about F here, we're talking about U. So that's why my brain is like going, what the fuck? But this is about U double prime.
Yeah.
Because U double prime is F. Okay. So the approximation here would be huh. No, we're not talking about the difference is not in U prime because we know. No, wait, we don't know U. We know F. Okay, so the okay, yeah. Sorry, I'm figuring this out as we go.
Yeah, I think we have to.
So I feel like so we need to get this approximation. Because it says using A and B, right? And A is the one where we figured out the actual solution, so the exact values are needed, and this is how we get the approximations. So this would be. It's just weird to me that this approximates F, not U double prime.
It's the same thing.
Well, okay,
Your
but
F
we
there is
want to
just misleading.
True. So U double prime and F are the same thing, but we want to approximate U. So
Yeah, but we can. We know that the difference between minus U double prime that we find numerically or the real is just the order.
So
which is
so
the
to do
Taylor
that,
Swift. It's the fourth Taylor Swift. Taylor Swift. What? Taylor series.
No. So the thing is, we can't compare this stuff to our exact values because this doesn't give us. So our exact values here are for U, or for U, not U double prime. Because this is an approximation of U double prime. Look at the exam again. Numerical value of the local approximation error for all grid points. So the local approximation error is what we approximate that the value of the function at that point to be. So what do we approximate u at that point to be? And what is the exact value of u? So that's the local difference, right? So yeah, I don't know. Yeah. First of all, I'm gonna replace all these F's with
Use.
with U's because looking at this is making me like it's
Yeah.
making me feel weird because that isn't what we're trying to do here. So I'm gonna just say I'm gonna have to copy this to Notepad because this thing doesn't have a proper replacement function that I know of. F to U X. And then here, and we go F X I to U X I. Now for the rest, we have F prime X I and F double prime and shit. And lastly, we have X or F of Xi plus 1 becomes U of Xi plus 1. And minus 1 becomes minus 1. So let's hope that didn't... I don't think I used this notation anywhere else in my calculations. Oh. But there's even some F triple primes, for fuck's sake. Okay. So let's see if what I did makes any sense. Yeah, okay. That looks better. Just use. Okay. So now we know what we're actually dealing with. Although I did fuck up with some double primes here. I think I replaced all U's with U double prime in the last two rows. Oopsie. Yeah, okay. This makes sense again. Lovely. So, then so we have the exact value of U1, but that doesn't matter here.
No.
Like, we can fill in these, and that will give us a value that approximates F. So, we can see how well we approximate F, but... Okay, so what we could do is fill in F here, and the actual values of U here, and then see what this comes out to. right? Because we know f at all of these points. So we can do this, we can do these, and then we'll see what OH squared is, because OH squared, that's the error term. That's the thing we want to know. So yeah, then what we'll have is so what I can do is just first of all take these. And also says all grid points, so I can just go for u0, the exact value is 1. And for u5, the exact value is 1.
BRB.
Sure. The method's maybe a bit unorthodox, but I think the number that I'm getting from this should be correct. Now to actually calculate this garbage.
Figure it out.
Well, not exactly. Well, sort of. Also, fuck that. I'm just gonna work with approximations. I don't care anymore.
Yeah, this one I don't know, and I can't even find anything on slides or anything.
Yeah. So what I'm doing is I'm like using these equations we have up here, even though it's part of C. So probably not doing it perfectly. So Yeah, what I'm doing is I'm saying, okay, we're making this approximation, and because our a vector comes with like h squared of imprecision, I'm just saying make this approximation, and see what those e values are, the errors.
Mm-hmm.
And I'm kind of lazy, so I'm not gonna write it out completely, even though they ask it for it exactly. I think. No, the same numerical value. Good enough. So 25 times u2 is this thing times 25. So minus this. Oh. 25 u1 is this. 25.413. U2 is 51.56, and 25 u3. Yeah. Like, I don't know what if this is what we're supposed to be doing, but honestly, it's like worth a shot. 25.98. And then here, 25 u2 is this one. Uh, 50 u3 is this one, and 25 u4 is. Yeah, it's still weird to me that this isn't symmetrical. I really feel like it should be. So I think I've done something wrong somewhere.
What do you mean symmetrical? The error should be the same everywhere?
No, actually, x squared isn't symmetrical from 0 to 1. No, never mind. It doesn't make sense that, it makes sense that it isn't symmetrical. So yeah, I was talking about like how not the error should be the same everywhere. It's that so it's that the value should be the same everywhere, but like it shouldn't, because the function that we're talking about isn't symmetrical. Okay. So now we have our error values at every point. We know the error at 0 or at 0 and 6 is, well, 0. And now to actually write this to something determinable from alpha plus minus plus. Well, that should of course be the absolute value of this, but like whatever. Okay, and now I should be able to just throw this in Wolfram Alpha and get my results. Which, holy shit, this is not worth the points. This is like a 1-point exercise. Which probably means I'm doing something wrong, but, well,
Probably.
here we are. At least it's like still, you still have to like know this. Still make sense, or you still have to make it make sense. So these should all be not negative, but error. Actually, what I'm going to do is I'm going to just extend these the numbers that aren't precise by a few decimals. Yeah, okay. So this is the error value. Interesting. Yeah, they seem to have the same error value everywhere. Probably means I did something wrong, but... And honestly, this might just be the imprecision of my like writing shit down. But it seems that all of them have just the same error value.
Yeah.
Oh well, maybe I'm wrong, maybe I'm not. We'll find out when we check the answers. Next question.
Yeah, error usually is given absolute value also, I think.
Yeah, true. So I should. And then, like, I probably should, like...
Can you remind me where you got the value for U1 and U2?
So I got those from my actual calculations, because I know from the exact numbers that this is the solution to U.
Yeah.
So that's the only reason we're able to calculate the error, because we know
The exact, yeah.
Yeah, we know the exact values. So yeah, my way of writing this is probably horribly wrong. Because I'm just suddenly adding absolute values, but oh well. Okay, we have answers at least. Okay, use the following boundary value problem. Oh, fucking... Okay. Right, they really want us to know this shit well, don't they?
This one is gonna be interesting.
Yes. Pi I plus 1, qj plus 1. So... yeah, these are the grid steps which are known but not equal, so we can use them to write shit out. Discrete equation of the vertex-centered finite volume method located at the skewed part of the boundary. And J, K, and G are known, and this is the normal at the boundary. Right. So the difference between finite boundary and finite volume is that we're fucking is that we're integrating over the edges, I believe. I'm just gonna try look at this and try and see if I understand. But like,
So maybe with the slides.
yeah, I was like, I'm probably gonna need the slides.
So this is like almost exactly one-to-one what's happening here.
Yeah, just mirrored, but yeah.
Yeah. I'm gonna grab the actual slides because this is just...
Yeah.
They really want you to
Fantastic.
know what's going on. Yeah, sure. Thanks for being here. Goodbye.
Goodbye.
Read this real quick. Um, yeah, so applying finite difference approximation of the double derivative, as one does, which is the same that we're doing here, except for in 2 dimensions. This steps to solve it. Yeah, so it's applying the integral over a certain length. Or well, on the boundary, I believe it's the integral over. No, I think everywhere it's just the integral over a volume. So here it's integral over a length, but anywhere else do the integral over volume. So here it would be the integral over, or going from here to here. So you have this like sub area, right?
Yeah.
So this skewed sub area, it'd be the integral over that divided by the area of that. So that, because that's what you see which they do here. They're dividing by the area. And they're saying that's the same as the as that for the outer sides. Although I believe you can multiply away that. I don't know. So they're asking. Yeah, just give the one equation for this point located at the skew part of the boundary. So first thing I'm just gonna write down the boundary equation. Might be complete bullshit, but I'm just gonna do it. Because that's how so far all of my answers has gone, and so far I think I'm doing reasonably. So it is negative k nabla u c dot vec n plus omega sigma balls u equals g. Okay. So this is the equation that we should be trying to solve. So the equation that finite volume tries to solve is the integral, or in this case but we're in 2D. We can use a single integral. The integral over the boundary, so over r power to the boundary. Yeah, I now have to write down r part of the boundary. So for now, I'm just gonna go omega. I mean, no, I'm still correct when I say that it's the integral over delta omega. Yeah, so that entire thing, d vec. What do they use again for the outside perimeter? Yeah, they just use dx, but on the 2 dimensions. dv.
Mm.
Yeah, fair enough. So dv. Although no, I'm thinking about the yeah, so this is just the integral over the outside where this over the boundary. So yeah, here right now they use just the symbol for the boundary. I'm just gonna call it S. I don't know why, but it now is S. over delta omega d vec s. So I believe that this is kind of the equation that okay, I'm just gonna use double things because I need my space here. I believe this is the equation that they're trying to solve. Or that this boundary volume method is trying to solve. Yeah, there's probably a C dot somewhere at the end. Okay. Hey.
Yeah.
Bro, what are you doing up there?
C dot. Ah, what?
So, oh, so I forgot the C.
Oh.
Okay. So, right. So this is what we're trying to solve here. So yeah, you need to divide by the volume of the cell for true averaging. Whatever. Yeah, so you can see when there's a straight point, what they do is they split the boundary into segments. So while iterating over the entire outside, we will iterate here in our exam. We'll iterate over this, this, and then this skewed side, I think. Right? Because like
Yeah.
yeah, what we're doing here,
Yeah.
I'll get it into Paint so
Yeah.
we can do oh, fuck off.
Whoop.
We can do this, and then I'll crop. So yeah, what we're trying to do is we're trying to make our own small area, which goes from a half to down here,
Yeah.
to half down here,
Yeah.
and this,
Yeah. Yeah.
and then we divide
Yeah.
over the area of this thing. So yeah, that's kind of our integral. So yeah, we integrate over the actual. So wait, do we integrate? Oh yeah, so they use the they use the divergence theorem. Yeah, no, that makes sense. So what they do here is they apply the divergence theorem, and then it becomes it goes from the integral over. So right now this is the integral of the area. This is not yet over S. This is both over. Well, right now it is over V, but I don't think that's what they're doing here. So here. Yeah, they're going over the entire volume on the other side. So, yeah, sure. So this is still over a volume. And this is over. I think this is over omega, not delta omega. No. Yeah, okay. It's over that small volume. That they're talking about. Yeah, sure. So this is over the volume of the cell. So they integrate over the volume of the cell, and then this is for now also over the volume of the cell. Ij, and then they apply the divergence theorem. So this goes from the entire thing to just our cell. Although this isn't over delta omega. Well, is it not? No, I don't think it is. This is over. this equals f. Okay, so this equals g, but they're okay. I'm gonna be adding multiple fucking things. Yes, what they're probably doing is that they're gonna be this part is gonna be using the boundary condition. Yeah, and the rest is just gonna be. Yeah, so this is gonna be done using. Yeah. God. If I had taken this shit in earlier, I wouldn't be struggling this hard. But oh well, here we are. So yeah, we know that this is g. I'll just also write down the equation for f, so that I have that like laying around, which is negative nabla. Oh, I have this already. Negative nabla k nabla u. Wait, yeah. Equals f. So we know this. And we know that the integral over the edges of our small little cell is the same as the integral of the edges of our cell over what? Because you're integrating something. You're integrating. You're integrating f. Yeah, you're integrating over f. Yeah, and then at the edges you replace the integral over the edges by the boundary condition. Okay. So that's something at least. Y'all having to watch me slowly learn the fucking shit that I should have learned years ago.
That's good.
Yeah. So I'm integrating instead of over this. I'm integrating over f. Which is it negative nabla? Yeah, it is. So and this equals integral over f. Yeah. And then so okay, this is so far my equation, which I believe is correct. So we just take this, literally integrate on both sides. Then we apply the divergence theorem to integrate over the area on the outside. So instead of and V is here the volume of my tiny cube, or my tiny area. So this will become
Tiny triangle.
yeah, it's a triangle indeed. This will become I don't know. Let's name a fun letter. S. Sure, it's my boundary. Oh, although this has to be a V because it's dV. It's over a volume, and it's not a vector yet. We're working on that. dV. Yeah. So now this becomes vector S and vector S as we integrate over the edge of our tiny area.
And in reality, this should be like one of those integrals with a circle in it, but I don't know how to make those in LaTeX.
Yeah, me neither.
Integral with circle. LaTeX. How do I type a closed integral in LaTeX? Oh, int. Well, fucking sure. So int and int. Recompile. Hey, there we go. Fancy. Yeah. So this will be split up. Oh, actually, I think the right side just stays the normal integral. The right side doesn't. We don't integrate over the right side. Or we integrate over the right side, but we don't do it over the like edges of the right side. Because the left side can be split up into two non-boundary parts and a boundary part, and the right side can't.
Yeah.
Um,
Wait, what? The left side is boundary, right? The northwest part.
no, I'm talking about the left side of the equation.
Okay.
So yeah, the top left side is indeed a boundary, and the rest isn't. So yeah, I'm going to split this integral up into three parts. So it's the integral over S northwest ij, and this time it's over. So if I'm doing divergence, there should be another nabla, shouldn't there? Or let me have a look. Because when they go down,
But you did it. No, I mean, you did a divergence just to equate to f then.
I think this actually removes the. Yeah, so this is the part that like is rough to me. So they're currently trying to figure out their equation that they're trying to fuck with is the same as ours. Okay, so usually we go from oh yeah, so going. I see. So going to a going from a volume to the edge removes a divergence. It doesn't add it. So that explains why I was like, we're not gonna have three nablas. It does not like this. That's why. So this is over the northwest edge, but then this shouldn't be this. It should be this whole garbage. Although at that point, shouldn't another nabla be removed here because you're going from. I think this is minus KU at that point. Plus. Then it's the. So that's northwest, then we have the east corner, which is. The integral over the east of K nabla U. And then we add the south.
which is a wacky way of writing it, but I can't think of anything else I could do. So, and this S here is the normal at that point, right? No, it isn't. That normal is already like in here.
The
Why is
normal.
normal shop here? That's kind of my question. If they apply the 2D divergence theorem.
I think just for the sign also, depending, but it's gonna be negative anyway.
Yeah, whatever. For now, we'll.
Yeah, I don't know, but I remember. I don't know if you did, if you had electromagnetism.
No.
But there also you have to see the Gaussian whatever. You also do this closed loop integrals, and it's d normal also to the surface. So
So yeah, here you can see what they do is they split the boundary in 3 sections,
yeah,
which is what we do.
then put the boundary conditions. Yeah.
Yeah. Right, and they're going over dy and dx for the non-boundary conditions. Sure, that does make sense.
Yeah.
So for this d, or for these two, we are going over ds. So this is east, and east will become. That's fucking. So that's dy. Yeah, I guess up and down. And the other one is dx.
Yeah. There's also a difference between this exercise and the example in the slides that it's not uniform grid.
Yeah, but that
Also
only
that.
matters when we're calculating with
Yeah,
aces.
yeah.
So the example in the slides, what's their boundary conditioning then? I think their boundary condition only comes into play.
Yeah, this
Yeah, their boundary
output
condition
is
only
blue
comes into
thing.
play like later. Oh, I see how this works. Okay, I'm up here. I'm spouting bullshit for like 1 second. So this here is not what I'm supposed to do. This still is just the integral over minus kW. But because we are on the boundary, we can then substitute what comes after. I was already looking at it weird that we were. That we did have to remove the nabla from the rest. But because minus kW at the boundary, we know that to be G minus OU.
This. Yeah.
Yeah. So yeah, okay. So this dot delta S can be expressed as like, I don't know, I'm just gonna call this ds and add a c dot vec normal here. Yeah, and then this inner part can be, because we know that this is on the boundary, and on the boundary this thing holds, so it's g minus delta u. So g minus delta. Did I say delta? I meant, oh my god. No. Which was it? Sigma. There we go. Sigma u. So we know that this is g minus sigma u ds. G min ouch. Right. So that now we know that.
Yeah. And then it's just the actual calculation here. So, at that point, yeah, the integral of f, I don't think you change. Huh. So I guess the integral of f is approximated by... Because so far we haven't like approximated the integral on the f side yet.
No, we.
So here they approximate the boundary conditions themselves. Oh yeah, here. So f
Don't even
approximates
understand.
to hx hy over 2. Which probably is explained somewhere, but I'm lazy.
I wonder.
Yeah, so what? Actually, I'm not lazy enough to know this. I want to know this. Why is fy or f or the integral of f approximated to be that?
Well,
Oh, so because usually the approximation for the
rectangle.
it's just the volume.
Yeah.
So,
Of a
well, it's not
rectangle.
exactly the volume because it's the
And this
integral
game is a
over.
triangle.
So they're
Yeah,
just
so you
saying
divide
we
by
take
2.
we take the middle value and we take the volume of that. By the way, these should be double integrals, not single. And yeah, okay, now that makes sense. They just like say we take the area and we multiply that by the actual value at that point. No, yeah, okay. Lovely that at least some of this is making sense to me. It's always a very welcome addition. Okay, so yeah, this makes sense. Take away one of those, continue. Yeah, okay. And then this right side I'm going to approximate with the... So because here again, we are taking, it's like literally over 2 because it's a straight line through a point. So it is Fij over 2. Or Fij times hx times hy over 2. And I'm going to make this a nice fraction. Right, so it's the right side approximated. Now for the left side. Left side approximated by, let's do the boundary condition last. So this is the... So this is minus k nabla u. So, yeah. And nabla means like the single derivative. It's not exactly the single derivative, but the single derivative of a vector, close enough. It is ux over ui, or not over, it's a vector with ux and ui in there. How do we approximate that? It's not like it, so because it's only in one direction, yeah, it's only the east border, so it's probably minus 0.1 plus 0.2 over 2, right? It's the single direction, single derivative approximation, if I had to guess. Let's see if I'm right. So they're doing the yeah, okay. It's the approximation in one direction, yeah. Which is, yeah, hey, let's go. Okay, it's not over 2, it's over hx. Yeah, because the over 2 part came from, no, that it never was over 2, it was over x, right? Okay, that makes me slightly more confident. That makes me happy. Where did it take the k value from? The k value is of course like in between points, I guess. Right. Let's see if I can approximate this shit. So I'm just gonna split the integrals up. So that I can see them better. Currently this shouldn't change anything about the formatting. Why is there two of them? Didn't change anything here, did I? No. Oh. Okay. So because this is the integral with respect to, but I think my writing is technically wrong. No, it's not. Yes, it is. No, it's not. So because it's still going over it's still integral over a line, so that line has a normal, and we're c-dotting by that normal. Like we're fucking. I think all this c dot dy and c dot dx, but c dot must go because it's not a vector. Yeah, okay, I think we're at the point where we're making sense again. So this is ds. Here my fucking dx just completely disappeared. What's going on there? Oh. Okay. So let's have a look at this approximation. So this approximation would be, this is the southern side. Yes. So this would be K. Just gonna try this. Fuck it, YOLO. So southern side is K. IJ, and which one goes down? It is J minus 1. It's K, I, J minus 1. It's a fraction, of course, because we're dividing by one of the h's. Which one? That's a good question. It is h. I. Yeah, and the normal here is 0 minus 1. Yeah. So the divide dx is the only one that remains. Makes sense because we're going in a southern direction. And the divide dx is it is g at f at location I j plus f at location I j minus 1 is one of these negative, probably, that I do not know. Yeah. So because this whole thing is negative, because we're going south, this thing is negative.
Always negative?
Hmm? No,
This thing is all.
No, it's because we're going south. So, yeah, here you can see like there's negatives for east and north, but because you're going south, you're already flipping the sign of yeah, so stuff like this, because on the west and south boundary, you're multiplying by the normal, which is negative, so you get a negative.
But what is the direction that we're going? I understand if you go against the normal,
right
you
now
go
I'm
from the
going just
point.
the east and the south. So in the east,
Yeah.
we're going east, and for the east boundary, the normal points east, and for the south boundary, the normal points south. Right? Because if we look here.
Yeah. Always
here,
outside. Always points out. Yeah. But then where are you going from to where? So I know why sometimes it's like this. So you go from where you wanna to. Okay. So then you're going.
I think so.
Okay, going south, you're going the same direction. Going east, also in the same direction.
So I'm currently approximating. I'm currently approximating the
the derivative on the y-axis, so d u dy. I'm approximating this from this point with information about this point.
Okay.
So usually that would be, and I always forget which one is negative. So because we want to know, what we had was the negative nabla. So the negative nabla is the same as the middle one is then. I always forget this. If it's positive, then the middle one is positive. Okay, I can remember that, which makes sense actually. So then what I need to, or then it is the middle one is positive and this one is negative. So then my approximation, this should, okay, so this would then be my approximation for S, for the south boundary.
Mm-hmm.
Because this is the, is south boundary dx or dy? Oh no, it is dx, but the
Dx.
yeah, because we're, the boundary is over dx, but we approximate the boundary by the derivative in the y direction, I believe. Because we're going south from our point. If I look at the slides at least. So south is a dx, but we're approximating it with dy. Oh, interesting. I didn't know this hx term was in front of there. Well, I'll add that. Okay. So this is something I'm definitely just going to have to learn by heart. I do not have time to understand this yet. And there should be, these two should probably be outside of the brackets. So that it is down here. Yeah. So this is the approximation of the southern side. Then the approximation of the eastern side. So because we are going positive, then these two flip because there's a negative involved. So then I'm just going to copy this for convenience sake. But this one will become minus ij, and this will become I plus 1. Hy will become hx, hx will become hy, and it's I plus 1j. So, yeah, I just practically redid this, but in the other direction. So, it is hy times k plus 1j. So that is the k in the eastern direction, because this is the eastern side. And then I'm approximating dy, dk dx, or not du dx, good morning. I'm approximating du dx in the x direction, and yeah, because we're doing negative du dx, that is negative fij plus fi plus 1j. So this is the derivative in the x x direction, the positive x direction. Then with the ki plus 1 is because, well, that's the k that's still here.
Mm-hmm.
And the hy, I am not entirely sure what the hy is there. Gonna be honest with you here. I think that's because we need to average out the air, or because we're doing the area and not just the line.
Yeah, I think in this case, though, we can't use hy because there's no such thing, but yeah.
No, we can, absolutely.
Not,
because, like,
not uniform.
the grid steps are known, but not all equal. So...
Yeah, but yeah, so there's no hy, right? There is...
okay, so then I guess, so
there
these
is
are...
q,
yeah, okay,
qy
so
plus
then,
1 and qy,
okay, so then
for
they're
example,
asking a step...
qj.
Okay, so that's still doable, because we can just go... so...
Wow,
if
this one is difficult.
Yeah. Yeah, then what we can do is we can use... also, we're definitely not going to make this in time. But I'm also learning a lot here. So yeah, in the eastern direction, all hx's can be replaced by... hx here becomes b I plus 1. And the hy... Honestly, I'm not sure what hy would be in this location. I think it might be qj plus 1 plus qj over 2. I don't think I'm correct, but it's worth a shot. So then this would be pi and pi plus 1 over 2 for the other one. Yeah. So this is b plus b over 2, and this hy here, because we're going south, would be qj. Okay. And then the f would be, yeah, I think just the average of these two plus the average of these two. Yeah. So that'd be times h this thing, and then also this thing. Yeah, they really want you to understand how this thing is derived,
Yeah.
which, well, sucks ass. Okay, and now for the boundary condition. So that will be approximated by so the way they did that is just go the length. So this length here is that's the square root of hx plus the square root of h, or the square root of hx squared plus hy squared, which was yeah, here they approximated by this, which is approximated by is this a skewed? This is a straight one. Like, give me a skewed boundary. So this is approximated by yeah, this function divided by the length of that line, or times the length of that line, which I guess is all the integral really is. I mean, not really, because it's still approximation, but I guess it makes sense that you just take the value at the midpoint of the line, which is this, right?
Yeah.
Yeah, take the value at the midpoint of the line, multiply by the length of the line. That will give you a approximation for the integral over the length of the line. Okay. So then this integral turns into just g sigma u. Let me just yoink these, because these are the lengths. So then this is g sigma u times the fraction of this one squared plus the fraction of this one squared, and then the square root of the entire fucking thing. And then I think technically this might be it. Jesus Christ. Okay. Oh, my QJ is, and my QJ and my PJ are not like tiny. Yeah, we spent like a full hour at this exercise, I think.
Yeah.
But like, this is the first time I've ever seen anyone actually do something with these, so this definitely taught me like a whole bunch. All of these now good? I think they are. Yeah, let me just put a new line here. Does it work? No, because it's a 2. Okay. Yeah. Right. 4 points. Makes sense. 1 page left. 8 points left. Consider the problem for the diffusion equation. Let A be the matrix obtained after the negative Laplacian operator. Derive the methods of lines solution. Did we actually have methods of lines in class?
Yeah.
Okay. Mm,
Yeah, this one I have no idea how to do on my own. Just it was open book, maybe.
is this thing open book? No, I don't think so.
No,
Yes.
no, completely closed. No notes, no nothing.
Yeah, so
Yeah, this method. I don't think you can come up with it without the slide. Yeah. Then is that all that bullshit that given that A is positive definite, then there exists whatever pre-matrix V lambda V inverted.
yeah, so this is like doing methods of line stuff where you take the square root of the fucking yeah, this. But maybe they gave an example on the board, but because I wasn't there, like
Yeah, this with FDM FEV, you have this there. This is it. The beginning there.
yeah.
Assume A equal V lambda V inverted exists, then
So the
yeah,
reason
this is exactly it.
the reason that like the reason that we can split this up, I guess, is because it's positive definite, like this VB thing.
Yeah, that you can do A V lambda V. Yeah.
Yeah. So this and then this. Yeah. But good lord, do I not understand why this is possible? Like, okay, for every point, it is the eigenvalue.
This is for the diffusion equation that you're looking at.
This is for
There's
this is for the negative lambda u. Yes, vector A. Never even fucking heard of it. A and D. Yeah, no, so this is an example. This is not an explanation. I feel like this might have been explained more thoroughly in their, in 2019. Honestly, I'm planning on skipping this just for the sake of time as well.
yeah. Yeah, there is a, if you go to in the slides, if you keep going down, I think there is a method of lines for the diffusion equation, which is the case.
Yeah, so we can copy the
Yeah,
fucking thing.
it's exactly just that, but well, can't use the slides.
Yeah.
This is fucked up because I'm just gonna have to memorize this without making sense of it.
Yeah,
for a
I
chance
really
that
hate
he's not
doing
even
that.
gonna answer. He's not even gonna ask it, and he's just gonna waste my hard drive and my brain.
Yeah.
Memory space.
Like this is also gonna go straight out of the brain the moment I'm done with this course.
Yeah. Then you're gonna skip the whole question 5, or you're gonna try B where he
I'm
asks for
gonna
the.
have a look at B and C.
Yeah, he asks for the pseudocode for the Euler method. For the Euler.
Pseudocode of forward Euler with the approximations. Okay, that one I do know. That's because we had to like actually write code for that. Skip. Sorry. Item. So.
Yeah, this you don't even need to share this with anybody because they have the answer anyways.
Yeah. So I'm just gonna write down the formula of the forward Euler by heart and see if I'm correct. So u k plus 1 equals u k plus, and here it was dt for your time step times, or well, I think 1 over t for your time step times the derivative of u at at time k. Which might be wrong.
I 1 over t.
I mean,
think just
this
dt.
could be wrong, but the way I
think it's just
remember it
dt.
is you do this, or if dt, you can also write this as dt, where it's like dt is the time step size.
Yeah.
I feel like this was forward Euler, so you
And
would have for pseudocode.
the derivative of uk is au? No.
Yeah, because I mean, so technically this is the this is that, but they had indeed a way to actually get the derivative in a way in code. So I believe that wasn't here. I believe that was in the previous lecture. Yeah. Forward Euler. Yeah, so UTH plus F, where F is for some reason the fucking the UDT. Like, why would you call it F? That is a horrible, horrible name. I guess no. I guess it's just an example. No.
Yeah, I think this FTK UTK is out the matrix A times UK, right?
Sorry.
You have there forward the Euler iterations UTK plus H approximate UTK plus H FTK UTK. Yeah.
Yeah. So
I think this FTK UTK is just
the derivative.
the matrix A times. Yeah.
Well, yes, it's so the reason that it's A times, that's like seen here. The derivative of u is minus
Yeah,
H.
exactly.
Yeah.
Mm-hmm.
Although then you must have an A that actually fits there. Because like there's a different A for double derivatives and for single derivatives. So yeah, just make sure you have the right A there. So yeah, then the code would be so while u while the u is our is what we hope to be the how long do we go? I guess I'm just gonna go while n or index or iteration less than nt. Actually, I'll write this back against the wall. There we go. Well, iteration less than nt, or I'll do a equals get get derivative discretized derivative matrix, fancy name. U is u start. Then while the amount of iterations isn't done yet, u is u plus dt, or 1 over nt times a u.
A get discretized derivation. Nice.
Yeah, I mean, I think this is just forward Euler. Yeah, I'd have to check, but here what they're doing is, oh yeah, I need to throw a negative in there. Because AU is positive, and we want positive here. Yeah. I think this is working code for the forward Euler method. I think I also completely butchered the word discretized. Discretized. Yeah.
That's correct.
Discretized.
Right, why?
There we go.
Did crit. Crit damage.
Oh,
Made it worse.
yeah, I made it a lot weird.
Still wrong.
Fuck. Discrete. Yeah, because it's discrete. Discretized derivative matrix. You start and continue iterating. Alright. If our right, this one should be doable, sort of. So if R is in R3 and lambda is a rectangular parallelepiped.
Parallelepiped or parallepiped. No, I think parallelepiped.
I don't know. I think so.
In Portuguese, it's parallelepiped.
Then
So
for
yeah.
the triple uniform grid with grid step h, the eigenvalues of the matrix are given by this. Okay.
Yeah.
So, but I think so. I remember.
I think that time step has to be smaller than the max lambda divided by 2 or 2 divided by max lambda, right?
Yeah.
But I think we need to derive that for.
Yeah. So I have derived the stability before.
Yeah.
So
It's
it
1
was
minus ht has to be smaller or equal than 1.
Yeah. So it's if I look at so if I look at the math here, it is u k plus 1 equals u plus ht plus, or u plus ht times minus a u, or u k. So to stop this from spiraling out of control, auk, the size of that needs to be less than 1.
Yeah.
And we know that that is the case due to method of lines. I have derived this before with the help of method of lines, but I'm not entirely sure how.
I mean,
So I think it was something like
can't we just say that we know from forward Euler that the absolute value of 1 minus h lambda? Yeah. Deriving this with method of lines is impossible. I mean, it's possible, it's in the slides, but
not for us, not right now, not here. Because I know that if we do this, well, that isn't exactly accurate. Because we're missing the HT here. Right? I'm just gonna, okay, I've done this before. I'm gonna look at my derivation in...
yeah, just sent on...
hand in time is already passed anyways. I don't think it's illegal to look at this.
I sent to you on Discord on the chat here also.
Yeah.
I think if they ask this exam, you can go directly from the absolute value of 1 minus h lambda is smaller than 1. It's very lucky if they ask stability condition of forward Euler, because it's easy. Now if he has to prove unconditional stability of the other ones, impossible.
Yeah, so I do like to write down this at the very least, so where it's like, this is u0 and this to the power k. Therefore, I minus ht to the a, or hta to the power k needs to be less than 1. And yeah, and then from method of lines. We know 1 minus ht lambda. This can diverge if max of this all, so lambda j greater equal 1 or greater 1, and it's the max over j. Therefore, we need to know that, or therefore, this is stable if but okay, no, I'm going too fast. Yeah, fuck, I'm just gonna go like quicker. I'm gonna go that I'm gonna just say 2 over max over j of lambda j. So if 2 over dt or ht is greater than this, therefore it's stable than if it's less than this. So if and from this we can say that it's sine, so it's 3 over, yeah, so sine squared is maximum of 1, so it's 12 over h squared is the eigenvalue. So that will become max j is 12, then this becomes 1/6, and h squared. Yeah. Oh wait, there's a 4 there? No, that's the 12, yeah.
Okay, so that's the stability of our method. We know it's stable if HD is less than h squared times 1/6. Right? Yeah, so we know this from the slides really almost. Consider the following problem for the Zeldovich equation. Never fucking heard it. Okay, so this is kind of my Achilles heel. I do not know or understand. So I understand the backward Euler part of this.
Yeah, but the Jacobian?
The Jacobian and the Newton-Raphson part is where I'm like,
No.
yeah.
Yeah. This I have to completely go over everything.
Hello. Scalar addition. Yeah. Okay, so this is pointwise product and sure pointwise addition. Okay. So yeah, we know about this. Where f is the derivative of u. So backward Euler is the exact same thing, but instead you're using uk plus 1. So you can get this, or you can get this by rearranging if you rearrange this, like the if you take the fucking antiderivative or the opposite of this f function and apply that, then you can get uk plus 1 all to one side and uk to the other side. So here you can see that how they do that by no Picard. Holy shit. Yeah, so here is what I said, where you take the inverse, so you can get that UK plus 1 out of there. Oh my lord. And the Jacobian is just the derivative.
Maybe I was gonna say maybe we can go over the answers.
No, so I still want to like give this a try.
Okay.
And then we can go over the answers. At the same time, we are
This
at
one I
3
don't even know how
hours.
to touch.
So, derive the Jacobian matrix. That's rough. That's not gonna happen. Because they don't even like give us the Jacobian matrix, right? They also just go
No.
fucking. This is the Jacobian matrix. I mean, so they actually that's not true. They do say here that if you so I believe that this is where you take the give me a second. Yeah, 1 minus this is rearranging. So yeah, they just because of the Taylor expansion, they have the first level derivative of u with respect to or of f of u with respect to u. So you can see this as u, the derivative at point u. or at point UI. But that's a fucking wacky thing to get. So I'm kind of trying to visualize this, right? The derivative of the function with respect to itself, or to the input. Yeah, so I believe that this is their that wacky thing they did, where if you take the derivative with respect to a vector, then it is like the derivative with respect to each of the components of that vector.
Gradient, you mean, or the divergence?
I do not know. So I think that's the thing they're doing here. So the Jacobian is just. But what's the difference between the Jacobian and the gradient then? So it's FQ. What is FQ here? Oh yeah, because F is like a whole
Yeah,
list of functions.
yeah. In this exercise, the F is this,
Is the derivative.
yeah, AU plus U.
So it's the derivative of F with respect to U. And since F is a whole list of functions, it is the derivative of F of the function at index I of or index j of F at index I of U. So that's why there's a 2D, or it's a 2D matrix, because the function has j inputs and U has I elements. Oh my god. Okay. Yeah. So that's how. So you would derive the Jacobian matrix just by literally copying this one to one. So I'm just trying to like, understand.
Not gonna
this.
happen.
So this is just the function at that point. This is derivative of that function at that point times the times h plus some stuff. So we fill in like into this, we fill in this approximation, multiply h out of the brackets, subtract the UI. So far what they're doing is still not completely vague. Putting the UI and V forward, putting this backwards. They're not really doing jack shit here. Well, there's just yeah. No, okay, they're pulling this towards the other side of the equation, because there's a U minus UI there and here. Then they take this out of the brackets. They take the U minus UI out of the brackets, because this is just a multiplication. And then they take the reverse of this giant matrix. So they take the reverse of I minus j. And then times this part, because that's like what remains after the rest of the function. Okay, and that is yeah, and that it makes sense that is like U minus UI plus UI is U. So that's what how you get this. Okay. I slightly understand Newton-Raphson's now. It is just like the yeah, it's just like space decrystallization. I mean, that is what it is almost. It's just you have this function and you take the Taylor expansion of it, and you you cut off the h squared terms. Yeah. So what was the question exactly? Write down the
Jacobian
pseudocode.
and the pseudocode.
Yeah. Write down the pseudocode of the backward Euler-Newton-Raphson method. Fuck it, sure. So while so J is Jacobian, and to get to the Jacobian you need F, you need U. Is it Jacobian? Do you need to calculate it per thing? Yeah, you need it. Okay, so it's something I can't just calculate here. A is... I mean, we know what A is already, but I'm just going to be like, guess discretize derivative matrix. So while error greater than error bound, do this. Oh, and U is U start, of course. So we want to have U is U plus H B. Yeah, and P here being H times the inverse of something plus... So the inverse of I plus or minus Jacobian U. So it's the inverse of that. And then you add V, which I believe is the derivative of U. What is V again? Okay, this is like the thing after. Yeah, okay, so that is... we are solving the... this can go. We are solving this. So U is... So this is FU. Okay, so FU is this thing. Then... So HFU plus V. Damn it, what is V? Oh, okay, so no, this needs to be rewritten to... Wait, what do I mean it can be rewritten as? Okay, now I was right. So FU here is this garbage. So FU is... Yeah, that. Fuck it, I'm not gonna write it out. Although... Yeah, so I'm gonna go FU is... Or def FU. Return A multiplied by U. Or negative A, because of course, for some reason this is negative. And then we get plus U times 1 minus U times U minus alpha.
at point u. Okay, so we have a function fu, we have the function Jacobian, which gets us Jacobian. Now what in the hell is v? Okay, so we already wrote down. No, we did. I didn't write down. Yeah, I did. No, this is forward order. Did I write down backwards order yet? Don't think
No.
so. So that would be UK plus 1 is, yeah, HD times F UK plus 1. So yeah, okay. So when they say any function can be rewritten as this, u is h f u plus v, that means that because the thing we want to solve is u is h f u plus v, v is uk. Okay, so then we know that. So here v is u. So u is u plus inverse Jacobian plus, what's it again? HFU minus u. So it's just HFU at this point. Okay, so we have u, and then we can use, so we can check the absolute error by do we just continue going, or do we have a way to check the absolute error?
Why check the error?
Because I remember seeing like, yeah, so while
Yeah. While
yeah,
the
so
error bigger
I
than
get,
whatever
yeah,
you give.
so I guess this error is this thing. So for me, that's
You
just
can just
HFU.
yeah.
Yeah, which makes sense because like FU is the derivative at this point. No, it's not. I guess eventually FU settles down. So while H times FU is greater than error bound to this. So that would be my backwards Newton method. Which is making a few assumptions, but at least it is
Something.
something, yes. Yeah, like for example saying just inverse. So close this, and this closes itself. Okay, time, even though I don't know if I'm very happy with being over the time of the exam, but at the same time I was like looking at slides a lot, so it's fine.
Yeah.
So exam answers.
Oof. Now let's see.
Yeah, let's see how hard we fucked up with the things. So let me just grab a Word doc to see, or so I can actually tally points. Word. That's Bing. Word.
How many screens do you have there? 2, 3?
I've got 3 screens. So delta E. Okay, so this is 1 point. Okay, I didn't put the fucking boundary condition there.
Oh, well,
No, fuck that.
right.
I'm just gonna. We'll remember that at the actual exam.
I hope. Bullshit.
Yeah, I did that at many other places actually. So the thing, they don't even tell us that there. Oh no, they did tell us that there was a boundary.
Yeah, they
Yeah.
did.
No, fair.
They did 4 different boundaries, yeah.
There were two
Yeah,
different boundaries. There was the
yeah,
E1
this
and
one,
the A1. So okay, so this is
the first 2 are correct,
EH.
and then the other 2, that's when you were doing, I said, yeah, it's almost correct, but in the answers, they have cross product instead of dot product, and I don't understand why. I don't know if there's something to
So I think
do
that this has to
with the
do with the fact that it's a
dimension.
curve instead of a thing. Yeah, this might have to do with the
Mm,
dimensions. We weren't taught this. I can tell you that much.
yeah,
So I'm just gonna find it good enough. Oh yeah, this has to be. This technically has to be the 0 vector. No, fuck that. Yeah, I'm just gonna say 0. Okay, so for 2, the problem can be written as
yeah, this one we did good.
according to theorem with the boundary entire function is positive.
Yeah,
Yeah, so by theorem 2. Yeah, by theorem 2.
yeah.
So yeah, that's for 2 we got 1 point. For B we said the minimum is on the boundary. Conclude
And
that.
he
Look
says
at.
about maximum also. We would get half a point
Okay,
there.
yeah. So they said do the minimum comma maximum, but I didn't.
Mm.
Yeah. Okay, we get half a point there. Sure, I agree.
Yeah, this is what I can't do in math though. Look at this answer. There is a maximum there if this and this and this. I
Yeah,
can't
that
remember all this
the
bullshit.
maximum is greater than 0, and it may be located if there is a point where. Yeah. So they say the maximum exists, and it is located in there
Inside,
inside if our function
if
ever grows,
minus f, yeah,
practically.
bigger than 0.
But
Yeah,
that's like
it just says obvious
that
shit.
doesn't really say much. So I do.
Of course, if
I
the
guess that
function
if the
goes
function
above
grows,
0, of course the maximum is there.
so if the function grows, it is in the middle point, and if not, it's on the edge. So that's what they're saying there, I think.
Yeah. Yeah, but that's stupid. He's just saying the obvious, you know. If in the inside is 0, then it's constant. Yeah, I know.
Yeah.
You know, I just saying some obvious shit in math terms. I don't know. I never remember to do this, but yeah.
Yeah. Whatever. For
See,
now, we'll. Yeah. So they have. There's 2 solutions, which are both f. Wait. First, prove the solution.
yeah, this we didn't do at all. He proves that the
So
solution is just 0.
the maximum is on the boundary and it is 0. It's also super harmonic. Okay, yeah, okay. So if the maximum and the minimum are both on the boundary and 0, then the entire function is 0. Which means if the entire function is 0, then yeah. So because the entire function is 0, if the derivative is 0 or the divergence, then the rest. So this doesn't just mean that the entire function is 0.
Yeah, I don't understand, to be
But
honest. I don't understand why they say that it's subharmonic and why
so
there's a maximum and a minimum there. I don't
So
understand.
I know why they say that it's superharmonic and subharmonic. However, I don't. Did they? Yeah, they didn't tell us that we can use the fact that superharmonic. Oh, no, that's here. So if it is subharmonic, it takes its maximum on the boundary, and if it's superharmonic, it takes its minimum on the boundary.
Yeah,
Yeah. Okay. So because it is
but how you know
both.
it's both?
Hmm?
Why? How we know it's both?
Well, because negative. We know that negative. Let's see, it's not that one, it's this one. So we know that
Yeah.
for this one, let me have a look real quick. We know that the function. So the So this is smaller or equal than 0. Huh. You're right. It says it's smaller than equal. How is it
Yeah.
harmonic?
I just know that it's a
Yeah,
subharmonic.
it's super harmonic. So
So yeah, I just know that it's superharmonic. I don't know
yeah.
why he comes up with this that it's subharmonic and then it's zero. This I don't understand at all.
Yeah, I don't see why they say it's super harmonic or subharmonic, because I don't think it is.
Yeah, I don't.
Um,
But I think whatever. I think this for this to happen
yeah.
again in an exam is
So
such a low chance.
I think that if I think for 2 we have 1 point for C as well. I don't think we have like a full point there.
No. Only the second half. And we
Yeah.
didn't
So
even
they
say
say,
this V thing.
but so the thing is, they say that the point may be located in omega if it exists where this is smaller than 0. So it isn't subharmonic. So
Yeah.
oh, I see
This
what they're doing.
explanation of
No,
C.
I see what they're doing. So they are saying that if you have a problem where u is 0 and the boundary is also 0, right?
They're saying that
No, so they're saying that if you have a random problem, right? Nothing to do with our problem. If you have a random problem where
that delta delta
the
U is
delta
zero
u is 0
inside
and the
and
edge is 0,
yeah.
then it is subharmonic, f superharmonic. Therefore, it is 0 everywhere.
Okay, so this is
Right?
something else I should know.
Yeah.
I guess so. It's continuous. Yeah.
Yeah. So it's just 0 everywhere. It doesn't go up or go down.
But do we know that it's zero inside? We don't
So
know. We say it's
we do
bigger.
because thing u is 0, it is superharmonic and subharmonic, and because we know that it is 0 everywhere.
But how we know that this is zero?
So I'm not saying this has nothing to do with the rest with our other person. So say we
Yeah.
have one where u is 0,
Okay.
then
Okay.
there exists only one function, namely everything is 0.
Okay.
Then
Yeah.
you
Of course. This I
yeah.
understand. If the function is zero in the boundary and there's no gradient in the function is constant. Therefore, zero everywhere.
Okay.
This I
So
understand.
then if we
Then
take
this type of
if
function.
we
Okay.
subtract these two functions from each other, so u1 and u2, the different ones, the different solutions that aren't equal,
Can't be zero.
if you subtract
Yeah.
each other, then we get
Yeah,
this
this
function,
part
which
we
is equal
got.
to f, but f minus f is 0. So this is 0, and the boundary is 0. Yeah, because here we say u1 is 0 because this is the boundary here, and that boundary is also 0. So we have then the difference between the two is a function that is 0 on the boundary and 0 on the function itself, which we know is a fully 0 function.
No.
So that's what they're saying here, and that's the part we're missing. We said this, we didn't say this function itself is also superharmonic and subharmonic, therefore it is 0. So that's why I'm giving us 1 point instead of 2. Does that make sense?
Yeah.
Okay, lovely. 3. 1 point correct. Lovely. 1 plus.
Yeah. Nice.
Yeah. So this one is just using the Taylor series. We get this, we add them up, and this gives us this value.
Another
We also
point.
get that. Another point in the pocket.
Yeah. This
we
one was a free question.
Yeah. So here we get. Yeah. So that's what we say here. Well. I don't think I agree with them here. Oh no, I do. So they're still using 0 and 5. I moved them to the right hand side.
They
They did move it to the right hand side. How nice of them. Although, yeah, okay. So I did something wrong, which is the thing I did wrong is the fact that I did. So I said +1 here, but it needs to be +25. So this should be 25.
No. In your case should be +1 because you had the.
No. This needs to be 25 1/5, not 1 1/5. Because what I did to get here was I took this a, and I multiplied this -1 and added it to the other side. But a isn't just -1; it's -25 because of this factor here, and this factor here I forgot to factor in. So it should be 25. So I don't have this point.
No.
The matrix form.
I did.
Yeah, fair
But
enough.
I did the matrix after though. I think it's easier if you do the equations first. Just
Fair
I
enough.
don't know. You did the inverted.
Yeah, I just because I remember the matrix formula and from there I work. But so yeah,
Mm-hmm.
I think I got like half a point here instead of a full point
Yeah.
because I forgot that 25 term carries over to the right. Um,
Mm.
in our case, use this. There we have.
We got the correct answer,
Okay.
but we did a completely different way. Actually, the way we did is the way I would do, just trying to find
No,
the
yeah.
difference in
So,
the. But
um,
they just find the difference of the derivative. I don't even understand.
so the thing is, because we have a fourth power function, right? So
Yeah,
imagine this Taylor series. Imagine it goes on forever.
yeah. But it stopped. I
Everything,
understand it
yeah,
stops.
it
Yeah.
stops. So if we just
Mm-hmm.
expand the Taylor function until the moment where it stops,
We
then
have the
we have
exact.
we have the exact function. At that point, the
Yeah.
Taylor function doesn't become an approximation; it becomes the truth.
Yeah.
Um, so that's what they're doing here. So they're taking the Taylor function until it stops,
Mm-hmm.
and the fourth derivative of the exact solution is
Yeah. -2. Okay.
yeah. Although yeah, this is um, okay. So this is
Yeah.
minus two
-2.
everywhere, no matter what the
Yeah.
length is.
Just if you do the derivative of ux 4 times, it's -2.
Yeah, fair enough. So then the approximation error is um, so yeah, it is this thing which is
The double derivative of the exact solution
yeah minus our
minus the
approximation.
yeah.
So that removes this from the side, and we just get
But this
this
is my question. So because he asks for the local error, so this is the error in
at that one point.
the in that one point in the grid
Yeah,
what we found
with
and what is
respect
the
to
exact. But there he's finding the local error between the derivatives. I didn't know that this was supposed to be the same.
so he
Apparently it is.
so he's taking the local error between the double derivatives, and the double derivatives is the
Yeah.
f value.
Yeah.
Or well, no. So that's not true. What I'm saying. What he's doing is he is so when you look at this Taylor expansion, so we are using this, and this is the only place where we get error, right? If our Taylor
Yeah.
expansion continued forever, we wouldn't have any error.
Mm-hmm.
So, and here I is a grid point. So the only error we have is this OH squared
Is
term.
what's after. Yeah.
And this OH squared term is nothing more than minus u double derivative I minus this
Minus
term.
the other part. Yeah.
And that's how you get the
Okay.
local error, apparently. So yeah, that is
Yeah, much
this.
easier way.
Yeah, and then this 2 times 1 over 12 divided by
Yeah.
25.
Like that.
So
Yeah.
the answer I have is correct.
Yeah.
Yeah. So I think I would get. I mean, yeah.
Definitely would get
So I think
everything.
yeah,
Is
I am
correct.
correct. It's just
Yeah.
I did it in a very clunky way.
Yeah. I would do like you also if it was the exam.
Yeah.
But maybe it's good to remember this
Yeah. No, this is definitely
this
like a very
idea.
smart way to do it, and that's the way you should do it. Because I wouldn't have done this with that Wolfram Alpha.
With no. Well, you have scientific calculator.
Yeah. Okay, so for drawing the finite volume as shown in the figure. Okay, so that at least we've done, right? Because
Yeah.
this is my north, this is my east, this is my south.
Yeah. You did on paint.
Yeah, actually, it's still here, I believe. Yeah, let's go.
Yeah, remember, because this to me is a bit tricky because he never asks us to draw, but if you don't draw, you lose points. So
Yeah.
you just draw. Yeah.
Yeah. Poof.
Yeah,
Jesus.
this is long.
They do not
Alternative.
fucking skip over anything. So this part I've got correct. I just call it V. They call it omega. Sure. And they put the
Yeah.
negative outside of the brackets. So I didn't. Oh, so yeah, that's correct because if you just take these fucking these things at the bottom and move them here, this is correct.
Yeah. And
So,
just for you not to remember tomorrow in your exam, remember to put the dot between nabla and the other shit sometimes. Because there is a difference between gradient and divergence.
Yeah, so I do not know
This-
the difference.
Yeah, me neither, but there is. Because you see, there's nabla u there. This is the gradient of u, but the nabla of k nabla u is the divergence. So there is a difference, but I also don't know it. Don't know.
Yeah, I'm just gonna say the outer, because here it is you have to use dot product because you're working with another vector, and here the second one you have
Yeah.
to use the dot product. I'm just gonna remind that, like, the most outer one requires a dot product if you're doing the divergence, which is a horrible thing to do, and I recommend you to not learn that. But that's what I'm gonna learn.
No.
Okay, so let's see if the rest is correct. So I'm going here southwest or northwest of, yeah. So I'm saying my k. Yeah. So what I'm saying here is the same, right? So
Yeah, I
they're
think
saying ds. So d capital S, or yeah, this is a vector. Oh no, I'm actually saying that just right here. What the fuck? Yo,
Yeah.
let's go.
It's
Um,
split it.
so that point I have. Then let's see what happens
Yeah.
if we. So that's 2 points. Let's see if this shit is correct. So this one, Gauds, yeah, sure. Yeah, I didn't use this middle step, but I believe that this is so far what I have. So we use the derivative.
Scroll down a bit. I think if you scroll down, yeah.
Yeah.
Yeah,
So
I
this
don't think
is-
you're gonna.
I think I'm correct here because it's
You're not gonna get the point of the derivation because there's clearly a point there if you
yeah.
show the
I
derivation.
am missing a derivation.
Yeah, but I think the end result is the same. Very difficult to check, to be honest, but
Yeah.
well, there's a bit of
well,
differences there because it's I plus half, not I plus 1
Well,
in
where are you
K.
saying that? Oh, yeah, the k is I plus a half. Yeah, okay, fair. I'm giving myself half a point for that
Yeah.
because yeah, I did make a notational mistake.
But I think the
This-
rest looks correct, but it's a bit difficult to see with the resolution.
The rest is
but-
correct. I've checked it.
Yeah, okay.
Yeah. So I also noticed that I used qi and pi plus 1 here, which is I also did.
Yeah. And in the
Um,
real exam, I think it's much easier than on LaTeX.
Yeah. Okay, so I'm missing 1.5 point there. Sure. Maximum 4 points for 5. Skip. Since A is symmetrical and pulls definitely exists the I position, the
C Control V from the slides, this, and I
yeah, this is
can't
literally
memorize
Ctrl+C,
this
Ctrl+V from
fucking
flies.
bullshit.
Yeah. Okay, so remembering this is probably worth it. Just saying.
Yeah, but
Yeah.
definite positive, then this is true.
Yeah. Okay, that's half a point I left behind, but I do
Oh.
not care about the other half. Yeah. So I minus HT.
Wait, it's B that you
Yeah.
look.
So this one I have written down. So it's this I is literally just it's this one. This is what I've written down. U is this. Whatever NT is HT. It's a minus because a no wait, I do minus minus A or minus plus. Hey, let's go. I'm correct. Woo. Okay, so that's 1 plus. I love it when I'm right. Can I do it more often?
Yeah.
So the stability condition is
Yeah,
h squared
correct.
over 6. Yeah, this is correct. This is correct. I like the fact that they just instantly used
They
this.
started from there. Yeah,
That's
yeah.
nutty. I'm saying I have a point here.
Yeah, for sure.
And for 6, and now we fucking pray.
Nah.
So
Well, no points for the derivation.
this is the derivation. F. I mean, so what are they even deriving here? F UK. Because I mean, like this is given, isn't it? Hold on.
Well,
I mean, so do I give this in my? Yeah, F is minus AU plus U. 1 minus U. Yeah, okay. So I do that here. I don't give it mathematically, but I do give this F function.
Well, there's a bit difference also that it's K plus 1 instead of.
Yeah, so that's well, no, but they're never using UK here, right? So you can substitute this by UK and it'll work.
Okay.
The Jacobian at both I and J is this.
This I don't understand. I'm gonna learn this tomorrow.
Yeah.
Oh.
So this F stuff, I did not tell them how to get the Jacobian.
No.
So I'm missing a point there.
Yeah, this question.
So 4K. So they are doing it complete element wise, so row n thing. So I'm just gonna have to see if this is correct. Just for my entire thing. So I set I get A and get U. What, they didn't even use A? Oh, they use it in F, I guess. Yeah, they use it in F. What the fuck are they doing
I don't
here?
think the Jacobian bullshit that I don't know.
They are differentiating this entire thing with regards to k plus 1. Oh, that is funky.
I don't understand this at all.
So they are differentiating. So because it's df over thing. So they're literally putting f in here, and then deriving f with regards to uk plus 1. So they're just giving you a function for j. Okay, I didn't know you could do that. I didn't know you could just like. I thought we were gonna have to do this element-wise, but I guess you can just like create a function for jk plus 1. Okay, that's nice. Right. So, they just say. Oh. Okay, so I did this wrong. So what I did was I let my outer loop go until the error is too small, but the error isn't in the outer loop part. It is there's like an inner iteration, and that's this is the Newton-Raphson, and the Newton-Raphson is the thing that has a bound. So that's the thing which continuously improves. Yeah, and I also said while HF because their V is UK and not UK plus 1. So that's also something I fucked up. So yeah, here again this is V and they use HF, or I use HFU, but it should be HFU and then the previous U. Yeah, so the previous U stays, and then they keep iterating this because you're just to do one backwards Newton iteration, you're completely solving for, you're iterating over UI, but this one stays because this is like part of the previous thing. Yeah, right. I definitely didn't get all points here. So I got 1 point here because I described the f function.
Yeah.
So let's see. 4 plus 2.5 plus 3.5 plus 2.5 plus 2 plus 1. 15.5.
Nice. You pass. 24 total.
24 total? Okay. Over 24. Okay.
Oh, that's a pass.
Yeah. And, you know, I really, really, really hope that there's no minimum on the exam, but I know there's going to be a 5.0 minimum. And the reason I'm saying that is because I am fucking goated when it comes to these exercises.
Yeah.
Yeah,
But there is. I think there is. Because if there is not a passing grade, I can get 0.
Nice.
No, I can't get 0, but
Yeah.
how much we need?
We need a 5.8 for the total. Always.
Yeah,
every course.
Yeah, and I also think there's a 5.8 for the.
So generally it's 5.0 for exams, 5.8 for the entire course. That's 99.9% of the time how it goes.
5 from exam?
Yeah.
Oh, that's nice.
I mean, I don't know. That's in my study, computer science and engineering. That's how it's been for the past 5 years or 3 years.
Yeah, that's true. Yeah, but
maybe this is different, of course. Right.
Maybe it's doable.
Weird question. When do you think you're going to have dinner?
No, I think I'm gonna leave now. I'm gonna
Very understandable.
I'm
'Cause
gonna
I think,
stop for the day probably, and then tomorrow work up early and do the whole day.
yeah, I think I'm gonna do another exam afterwards. But yeah, if you don't wanna, you can just, I guess, watch the recording back.
Yeah.
Like, otherwise we can do it
Yeah.
tomorrow, but I mean,
Tomorrow I'm probably gonna go to campus and stay there the whole
exactly,
day
that's
studying there.
understandable. Yeah, okay, then you'll see this appear on YouTube, and yeah, good luck with studying.
Yeah, you too. Thanks for today.
Yeah, of course.
Thanks for the
for
other
the
two
help.
exams.
Yeah, you too. Thanks. Bye.
Yeah.
Cheers.
Goodbye.
Bye.
I'm gonna stop recording as well.